Hey everyone, and welcome back to this class, the Numpy stack in Python. In this lecture, I'm going to give you a small tour of other interesting Scipy functions. We're not going to look at many of these in code for a few reasons. First, if you don't have a theoretical background, then doing them in Scipy is not very meaningful. Second, we don't use these very often, only when needed, so it's not really useful to actually try them until you need to. The purpose of this lecture is so that you can know they exist and where to find them. It's also to make the point that this is not very hard. You don't need someone to show you how to use these things. If you got the hang of the rest of this class, you shouldn't have a problem with trying these on your own. They will probably work as expected. So the first function we'll look at is loadmat. MATLAB is a very popular numerical computing language in academia, so you'll come across it every now and then. If you're in school, you've probably come across it already. MATLAB has their own file format, which is the .mat file. These are not text files, so you won't be able to read them in line by line. Scipy comes with a function to open these files and parse them correctly if you ever come across a dataset that's stored as a mat file. In addition to images, another common source of physical data is audio. Audio is sound, and sound in its simplest format is stored as the WAV file. These files contain the signal amplitude at every point in time of the sound, and a typical sampling rate is 44.1 kHz. So that means for every second of sound, you'll have 44,100 integers representing it. You can load in these files using scipy.io.wavefile.read, and you can write them using scipy.io.wavefile.write. Very closely related to machine learning is signal processing. One popular signal processing function is convolution. If you've ever heard of convolutional neural networks, this is the technique that they use. Scipy has multiple convolution functions. You'll want to use scipy.signal.convolve for arbitrary signals of any size, but for images, which are two-dimensional if they are in black and white, you can use convolve2D. Also in the signal module are some interesting filtering functions. So filters are basically just waveforms that alter your input signal somehow. An example would be audio effects like reverb and echo and so on. Now oddly, the fast Fourier Transform, or FFT, which is also a very common signal processing function, is not in Scipy, but in Numpy, so you can already use it even if you're not familiar with Scipy yet. The Fourier Transform converts a signal from the time domain into the frequency domain. In other words, it'll show us the frequency components of the original signal. As an example, let's create a sine wave with multiple frequencies. Okay, now let's do sine of x, sine of 3 times x, and sine of 5 times x. Now let's plot this so you know what it looks like. Okay, so it's a periodic wave with multiple frequency components. Now let's do the fast Fourier transform. Remember that the FFT gives us a signal with complex numbers, so we need to find the magnitude before plotting it. So that's just np.abs. And let's show this. Okay, so that's the Fourier transform. Now if we zoom in, we can see the spikes that represent the original frequency components. So let's try zooming in over here. And we see 3 spikes. Okay, this appears to be at about 80. So let's zoom back out. This one appears to be at around 48. Zoom back out. and the tall one appears to be at around 16. So let's close this plot, and let's calculate what frequencies these represent. So that's 2 times pi times 16 divided by 100, so that gives us 1. 2 times pi times 48 divided by 100, that gives us 3. 2 times pi times 80 divided by 100, that gives us 5. Okay, so these are the original frequencies. So don't worry too much if you don't know what this means. I just wanted to show you that these capabilities exist within the Numpy stack.